Hello. Oh, sorry. Hello. Hello. Hang on.
Good morning.
Good morning. Oh, I heard that. Awesome thing. Wait, I heard it, but I was walking. Wait, I heard. Oh, Gabriella. Okay. Good morning. Good morning. I think. And Lunar. Good morning. And Jocelyn. Good morning. And Sydney. Good morning. Wait, and Weirdness. Good morning. Oh, wait, once. Who else? Melanie. Good morning. Okay, chat. Why? Hold on. Sinead, good morning. Teresa, good morning. Melanie for the double, good morning. Effie, good morning. Oh, there's more. Sorry, hold on. Norma, good morning. Christopher, good morning. Lunar for the double, good morning. Good morning, Sydney for the double. Good morning, Genesis. Good morning, Nadine. Good morning, Jocelyn. Why is my screen? Hold on, sorry. Oh, and I see Rebecca and Mohammed and Effie now. I couldn't see before. Good morning, and Jocelyn for the double. Good morning, Angelina. And good morning, Norma for the double. Good morning, Jean for the yes, for the yes. Good morning, George. Good morning, Mohammed for the double. Good morning, Gabriella M for the Gabriella M. Good morning, Joshua. Okay, I think. Yeah, all right. Um Okay. Uh, oh, and Alexis. All right, let's do this. Let's do this. Let's do this. I think, yeah, I feel like last class we actually got somewhere, which is amazing. So let's just keep trying to do that. What I want to do, well, yeah, hold on. What's on the screen now, is what was originally on the screen last Wednesday. But then we ended up doing so much, just not that. We ended up covering all these things that I'm really glad we did, and we would have covered afterwards, but we ended up covering before. So, so then hopefully you saw the PDF was adjusted so the title page to actually fit everything that we did, whatever it's worth. So now we're going to get back to what that title page to this title page. What am I saying? What I'm really saying is that we are going to talk about I'm going to switch the screen. We're going to talk about this. We're going to talk about this. So that's this, the most recent homework just due, a minute ago. Whether you're up to it or not, um, this is what we're going to talk about. We started with some examples on the prior homework. I want to just skip straight to this one. You'll notice though, so it's work. So I'm trying to shift my attention now to work done by constant forces to work done by non-constant forces or changing forces. It's all still the same topic, of course. It's work and its connection to energy. Um, and so it's not a coincidence that we're going to sort of look at the same example that we were looking at last time, something moving along an inclined plane. We're going to look at that same example, but we're going to look at it a different way, or we're going to look at what happens when some of the details are changed. Of course, the fundamental point, again, is that we're shifting our attention from work that's performed by a constant force to work that is performed with a force that might not be constant. Now, I'm going to switch screens again. So this is the context. So, okay, on a academic or logistical point of view, we're talking about this homework that was just due now. Um, that was just due today. Um, I'm going to switch the screens, but what I want to say is, um, you might remember that when I first defined work for us, I kept saying I'm defining work over a small displacement. Well, all right, let me switch screen. So now really what's happening here is we're generalizing. We're saying we're expanding the definition of work so that it could cover any size displacement. That's what's really happening. Even a displacement that is so large that the force might have room to vary. That's what we're doing. So I'm going to switch the screens back. So, all right. So forgive me. I'm going to switch the screen back. Okay. Okay. Right. So, right. For if a displacement is sufficiently, I mean, I guess really technically what I should really say is this. Like, you know, as long as the displacement is small enough that we can call the force basically constant, then the amount of work done is basically that force times whatever the displacement is. Okay, I mean that's what we've been saying over and over. Now, I want I want to expand this definition so that we cover more general cases, right? So I don't want to change. It's not that and I even understand there was some language in the homework assignment that sort of makes it sound like there's like two different definitions for two different situations. That's not really what I want to do as a physicist. It's not that I want to have two different definitions for two different situations. It's that I want one broad definition that is broad enough to cover all the nuances, right? So, um, so what do I do? Like, how do I cover this situation? And the situation that was in the homework, a person, Sisyphus is pushing this boulder up an inclined plane, but they eventually expand it to make it such that the force kind of changes every meter that Sisyphus pushes the boulder. So, like, how do I cover that idea? Well, the key point here is that the whole is equal to the sum of its parts. Sorry. Right. So the question is, how am I going to expand this definition to account for an unconstant force? Right. That's the question. Well, the answer, and tell me if you need me to go back. Okay, so I'm going to quick. So first of all, I want to say forces obey a principle known as superposition. This is an idea of physics, a principle. I mean, it's literally a principle. It's like a step three. Like if you were ever, this is something you would ever write down. You could write as a step three in certain problems, like say on the final exam, you could write forces obey superposition. What meaning that's true even before we start making laws or observations or experimental results about forces. Now, what does it mean to say that forces obey superposition? The principle of superposition is the principle that the whole is equal to the sum of independent parts. I mean, in English, colloquially, you've heard this, but the whole is equal to the sum of its parts. Like everything in physics, really, like every major idea in physics, this idea sounds stupid, possibly, when you first hear it, meaning the idea sounds so self-evident, right? That one almost doesn't even know why anybody bothers to say it, right? This is good physics. When we start with ideas that almost don't seem worth mentioning because they're that easy to agree with. If an idea sounds unnecessary to say, that probably means we all take it for granted as true. But then that means that we can build a whole system of thought on it, and the system of thought will be rock solid if we think it's that true that we didn't even think it was worth discussing. The brilliance of pointing out certain ideas like this, I mean, in my judgment, what makes the physics geniuses genius to me, and by that I mean, like Galileo or Newton or whatever, it's not that they thought of things that other people don't agree with. I mean, sometimes that was the case, but it's not that they thought of things that other people don't agree with or don't even think. It's that they selected certain truths, certain self-evident truths, as being the ones that really produce surprising amounts of unknown thoughts, previously unknown thoughts. So, okay, what I'm getting at here is that it's reason it's valuable to say that the whole is equal to the sum of its independent parts is that, in fact, that's not always the case. It's not always the case that in life, that the whole, really quickly, quick example, like if I can only grade 3 exams in an hour and my colleague, Dr. My colleague, Professor Liu, can grade 2 exams in an hour. If you put us together in a room to grade exams, I can grade 3 in an hour. She can grade, she can say she can grade 7 in an hour, right? If you put us in a room together, we don't necessarily grade 10 exams every hour, because once you put us in a room together, we may well interact. We might interfere with each other constructively or destructively, right? Like we might show each other tricks that speed up the grading that we wouldn't have known but for being in the same room. So we might, or we might chat a lot and slow down the grading, right? Like the whole would not be equal to the sum of independent parts if you put 2 professors together and ask them to grade. Or if you think that's not a physics example, you may know from prior experience, and you'll see a lot in physics 204, that if you put 2 waves together, the total amount of energy coming from those waves is different than the total amount of energy you would get if you just had one wave over here and one wave over there. So, okay, that's a quick. So often in life, the whole is not equal to the sum of its independent parts, but so that's why it's worth saying it when it is. Now, what's an example when the whole is equal to the sum of its independent parts? Forces. The idea of Newton's second law of net force, net force equals mass times acceleration. When we say net force, we mean the sum of all forces acting on an object. And the assumption is that if you push me to the north with 3 newtons, while at the same time you push me to the south with 2 newtons, then the total amount of force acting on me is like +3 plus -2, or whatever numbers I just said, and you get +1. Like the sum of the forces on me is literally exactly the arithmetic sum of the force vectors acting on me, which is to say, that each push that acts on me doesn't at all get affected by the presence of the other forces acting on me. It's actually a deep observation. I will move on, but I want to point out that when we say forces obey superposition, when we say that the sum of all the forces acting together is literally just this, when we say that it's that the whole of all of the forces acting at the same time is equal to the sum of each force acting as though it were independent, what we really mean is I can push you and you can push me, but I can't push a push. What we're really saying is that forces don't affect other forces. The presence of one force does not change the character of another force. Forces affect objects, but forces don't affect each other. They superpose. Okay, enough of that. Therefore, I mean, hopefully you sort of get what I'm saying. It's actually an interesting point, I think. That forces add independently. They don't, you can have as many forces as you want acting on something, and you keep piling on the forces. They don't affect one another. There's no interaction between the forces. But, okay, therefore, what does that mean? It means, oh, this is now brings us to the example in the homework. It means, oh, wait a sec. If work is force times displacement, but the displacement is so large that the force value keeps changing, can't we just say, and we can, what we could do if we want to take it to, if we don't have one F number to multiply by all of the delta X, can't we just say, oh, the total amount of work done for this large displacement would be like, can we just divide up the large displacement into a bunch of small segments? And how small? Small enough that each segment has its own appropriate constant F number. Couldn't we say, for example, if the force right here is 1 Newton for a meter, and then here it's 2 newtons for a meter, and then here it's 3 newtons for a meter, and etc. Couldn't we just say, oh, okay, 1 times 1, put it in our bag, and then move to the next one and say, oh, okay, now 2 times 1, put that in our bag. Now go to the next one. 3 times 1, put that in our bag. In other words, since forces, and only because forces obey superposition, because forces don't affect other forces, to compute So what we're going to do, and we do that. I mean, you may not realize. So what we do in theory, I'm just making. I'm saying, and again, that says that's not readable. It says, the theory here, and yeah, this is, I mean, the mechanism here is that if you have this large displacement over which force takes on different values, you, in your mind, in our mind, we divide the large displacement up into a bunch of small segments, each of which has its own F value. And so we do the F delta X product for each one of those partial displacements. And we just add up all of those partial work results to get one big work results. I mean, it's so, again, if you even are having the reaction like, oh my God, like, why is he explaining this so much? Well, yeah, okay, that's what I do. But yeah, it is as simple as you think. We're saying if the whole is too hard to deal with as one, divide the whole into parts but then add up all the parts. So we are saying so far, now we're going to use math notation for this. We're saying, my God. We're sitting right now. So I'm going to use a piece of notation. Remember from, okay, remember that, so that big symbol, that big capital sigma means sum of in math, right? May have been intimidating when you first saw it. It was intimidating to me, but let's break it down. Like whenever we use that big sigma, we're saying we're going to sum up, we're going to add up a bunch of parts of something. What kind of parts? We always use that sigma when what we're summing up is separable, discrete, i.e., countable parts. Whenever you have chunks that are divisible from one another, that where you can literally distinguish one chunk from the next and say, this is chunk number one, and then it ends. And here is the start of chunk number two, and then it ends. And here's the start of chunk number three, and then it ends. Whenever you can do that, the way you can do with grains of sand, but you can't really do with water. You know what I mean? Like water is just like whoosh. But sand, even though it's really small, you can be like 1 grain, 2 grain, 3 grain, right? So sand is what we regard in math and physics as discrete. You can distinguish between one piece and the next. You could literally count them, right? They're separable, they're quantized, you could say, as opposed to water, which is like continuous, smooth, infinitely divisible, right? So whenever we have a situation where the pieces are discrete, we use this jagged, like pointy Greek letter sigma. The pointy, jagged sigma stands for discrete, jagged, pointy sum. I'm serious about this because, again, if you might have been intimidated by this before, but there's a very specific purpose to this piece of notation. And then as you may remember from a math class, like the way you set it up is you put a little index at the bottom. You say, okay, my index for counting these pieces, I'm going to call I. I'm going to start my counting at piece number one. That's so saying I equals one at the bottom means like from here on in, the counting index is called I, and I starts with the number 1 and then is going to go on from there to 2 to 3 to 4, etc. And then at the top, we put this little letter N, meaning it's going to go all the way until the nth piece. I don't even know what that is in advance, but whatever the last piece is, it's going to go to. If you do know the last piece, then if you know there's 4 pieces, you'd put a 4 at the top or something. Okay. So then the point is that sigma says, I mean, maybe I should put parentheses around here. Then the sigma says, okay, we're going to do the following operation. We are going to go to the first, I set it 1 at first. So we're going to go to the first little piece of displacement, the first meter, let's say. We're going to ask ourselves, what is the force applicable to that first meter? Like in the case of the system, I really have to start tying this to the example I know in a minute. But, well, actually, I will. Hold on one second. Like in the case of that example, so I know I haven't answered the questions of that question yet, but I'm trying to give you the overview of like what's going on in that question. So like in the Sisyphus question of Boulder Revisited of today's homework, he starts out pushing the boulder with a force of 990 newtons. So in the very first, I'm going back to the Zoom. Okay. In the very first chunk, you would say I equals 1. Okay. I'm looking at the very first meter. Evidently, the force is 990 newtons. So I would do 990 newtons times 1 meter, right? And then what this sigma means is then you sort of put that in your mental bag. Like I've done one product. I've gotten the work for that one little initial meter. I've put it in the bag. And then now that I'm done with the operation, like there's nothing more in the parentheses, now I ratchet up the counter to I equals 2. So I go to the second meter. And now I ask myself, what is the force for that second meter? That's what it means when it says F sub I, right? It doesn't say necessarily that the force is 2. It just means the second value of the force that applies to that second meter. So according to this particular homework problem, according to the pattern they gave us, like he loses 30 newtons of force. So the next value, I mean, each time he does. So the next value is 960 newtons. So in principle, I would write 960 times 1 meter. Again, each one of these segments is 1 meter long. So I would write 960 times 1. I'd put that in my bag and then ratchet the index up one more, and I'd keep going, right? So, and I know in a way you know all of this. In a way. So the summary of what I'm trying to say is that if in life, if all of the situations were the way I just described, and if the homework problem were exactly the way I just described, then I would have just solved the homework problem and we would get an answer and we'd be done. And the way we would have just gotten the answer is by saying, oh, big work is just equal to the sum of small partial works. In other words, what I'm trying to say so far is we're not changing the definition of work to account for varying forces. We're just expanding it to say, oh, when the force varies, just do your work calculation one segment at a time and add them all up because the whole is equal to the sum of its parts. Like, why not? Right? And we're just using this fancy notation to capture the whole thing as a procedure stated as one equation. Okay, but now there's a reason that I'm sort of, dragging out the theory of this. That is correct. There's nothing incorrect with what I just wrote down. That is what work would be when we have to treat work as the whole sum of its independent parts. The problem is that's not actually exactly what's going on in the Sisyphus problem that you were assigned. And it's not exactly what tends to go on in any natural, real life situation. As many of you might have guessed, and perhaps might have confused some of you even as I was talking, is the thing is in life, forces don't generally vary in chunks like that. Life generally is more like water. Space and time are generally more like water than they are like sand, right? In other words, even in the problem, I just described it as though at each 1 meter chunk, you have a fresh new value of force. Like I just described it as though it was 990 and then 960 and then 930. But of course, if you read the problem carefully, that's not actually what happens. Right, hold on. I'm back and forth between two screens. I want to make sure the chat is okay. Okay, the chat is okay. What I'm saying is this is all correct. And it is what we would do if the force varied discretely. Like if it varied, but in chunks like this. Hold on. If force varies discretely. Now, again, when I say the word discrete, what I mean is countable, quantized, distinguishable. I mean chunks. Discrete means chunks, right? If, however, if the more, however, I mean, that's true. I'm just going to write it better. Hold on. I mean, if you were to wrote that, it's correct. I'm just putting it in different place. So the thing that happens in this Sisyphus example, and the thing that tends to happen in real life of space and time are continuous as far as we experience them at a macroscopic level. They're not made, as far as we know, of little chunks. Like there's no separation. There's no space between spaces, if you see what I'm saying. And there's no space between seconds or milliseconds. You can subdivide space into millimeters, but then you could subdivide the millimeters into angstroms, and you could subdivide the angstroms into milliangstroms or whatever, and you can keep going forever and never get to a borderline, i.e., space and time seem to be infinitely divisible. And what I want to say here, I'm saying a lot. What I'm really trying to do secretly now, it's not secret. What you might notice, the reason I'm spending all this time on this, I'm actually trying to teach you the calculus principle that is needed here. You have done calculus for 2 semesters. If you are anything like me, or like over 30 years of students that I've had to this point, it's possible that you've been doing calculus for 2 semesters, but never quite exactly maybe felt 100% comfortable with what it was you were doing or why. What I'm getting at is this. First of all, every single time in calculus that they make a big point and said, if f of x is a continuous function of f, or if f is a continuous function of x, like blah, 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 then the mean value theorem, blah, 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 blah. If you're anything like me, I noticed that they kept starting every sentence in a calculus class with like, if blah, blah, assume that blah, blah, blah is continuous over the interval, blah, 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 blah. And I didn't know what that meant. I mean, I knew the words, but I was like, oh my God, get to the point. Just like you're feeling right now. Yaverbam, get to the point. My point right now is the reason that you have to hear about continuous so much in a calculus class is that continuous means infinitely divisible. What continuous means is not finitely divisible. Continuous is the opposite of discrete. Continuous means things are not happening in chunks. In life, in nature, in space and time, things tend to not happen in chunks. space is continuous in the sense that you can subdivide it forever, infinitely. So continuous means infinitely divisible. And infinity means calculus. Once we're dealing with the infinitely large or the infinitely small, we're taking things to the limit. We're dealing with calculus. In other words, this Sisyphus problem, that you had for homework, this situation, it's not really the case. It would be fine if the force were one value at this meter and then a different value at that meter and then a different value at that meter. But that didn't really happen. A meter actually turned out to be not small enough to capture a constant value for force. I know that if I read the problem carefully because it says, uh, it says he gradually gets weaker as he climbs. For each meter he travels, he loses 30 newtons of force. So, like, that's true. For each meter he loses, but it's gradual. It's not, right? I mean, he's like, in other words, by using the word gradual, it's saying it's saying that for each meter, he loses 30 newtons of force. But in fact, if it's gradual, if it's continuous, if it's realistic, if it's any kind of realistic physics problem at all, yes, in a meter, he loses 30 newtons of force, but in a half meter, he loses 15 newtons of force. And in a quarter meter, he loses 7.5 newtons of force. You see what I'm saying? It's like no matter how far down you subdivide it, he's losing something. He's losing all the time. The force is changing continuously. So the question is, what do we do? What do we do? What I'm trying to do is take the concept, and again, I can't. This is why I get all excited about these things. We're actually trying to develop a fairly sophisticated idea here, an idea from calculus, right? And notation that's fairly sophisticated. But what I'm trying to show you, one of the reasons I talk so much about these things, I mean, yeah, it's partly just a bad habit, but it's partly that I'm really trying to show you, I'm trying to like derive or prove these complicated ideas. And I'm trying to show you that these complicated conclusions that we end up with, or these complicated looking notations that we end up with, really are the sum of small, reasonable steps all along the way. Every step of one of these arguments that we're making or these theories that we're developing, every step is supposed to be just small enough that you know exactly what I'm talking about, so much so that you're like bored. Like I don't want you to be bored, and I'm not trying to like trick you. But if it, and I know I do just to talk too much anyway. I'm working on it. I promise. I got 14 therapists and 3 textbooks, like all involved. Not really, but part of it is I'm really trying to show you that these complicated physics ideas are really the sum of a bunch of small, simple ideas all strung together. That if you can just hang with each idea, if you are willing to look at each idea and go like, oh, well, yeah, I knew that. Like, oh, that sigma thing just means the whole is equal to the sum of its parts. Oh, okay, that's fine. Like, if each step you could see like, oh, yeah, that's not, Then, and if you can resist the temptation to go, oh, that's all he's saying, well, then why am I even bothering listening? Like, no, yes, every tree is a tree you already knew before. Even the mean value theorem, for example, I'm not doing, but I don't know if you ever had that experience where the mean value theorem drove me crazy in calculus. I was like, what is this? What is this? This is so, what the heck? And then eventually I was like, wait, all they're saying is like for any two things, there's like always something in the middle. Is that, yes, that's all they're saying. Like, but they're saying it's really useful to actually focus on that. So what I'm saying right now, what I'm saying is if you want the whole amount of work for a whole amount of displacement over which the force varies, well, first thought is why don't you just divide it into a bunch of displacements, each one of which is small enough that the force doesn't vary? Okay. And then the notation that we use for that is a big sigma that means sum. Okay. But then we're saying, oh, all right, that's fine. So just divide the displacements into steps that are small enough to capture an unchanging force. Okay, but then we go, wait, what if? What if I can't do that? Like, what if no matter how small I make my displacement, there's still a little wobble in the force? Like, I make my displacements 1 meter, 1 meter, 1 meter, but the force is varying so much. Like, even in a half meter, the force, it didn't change as much, but it changed somewhat. So then I go down to a quarter meter. Well, the force varied a lot less in a quarter meter, but it still varied. So what do I do? What do? You take the whole process to the limit. You say, you say that the total amount of work for the whole mishpucha is the limit as delta x approaches zero of this whole sum. Right now, look, and again, this requires understanding limits, but we've been there. You like, what is a limit in science? I mean, I'm not going to get the whole speech again, but to say that the limit as delta x approaches zero, really, you could think of it as a very idealistic, like Smurf Village kind of thing in your mind, or you can be scientific and realistic about it and just say what the limit as delta x approaches zero really means realistically as a physicist. It means break this thing down into displacements that are big enough to matter, like big enough that a force did occur, but small enough that they're too small to register on your measuring equipment. That's what limit means. Like big enough to exist, big enough to have a measurement, but too small to distinguish from another measurement. Like it's between the cracks on my meter stick. So I know it's smaller than a millimeter, but I can't tell if it's a third of a millimeter or a half of a millimeter. That's what I mean and therefore, even though the force is still varying somewhat, the force is varying by an amount that's too small for me to pick up on my force meter. So now from a scientific point of view, we're talking about constancy now. If you can't measure the change, then there's scientifically then the change does not figure into our experimental results. So the theory here, well, I'm just making up. The theory here is that even if the force is varying smoothly, continuously as a function of position, right? If we divide the position into a bunch of chunks, you see where I'm going with this, right? I mean, many of you knew where I was going, for a bunch of minutes already. But if you see where I'm going with this, if this is starting to look recognizable from a calculus class, please stay with me because I know it's possible you might be starting to think, oh, I see where this is going. I hate this thing from cal. And I'm not look, and if you don't hate it from good, Quark bless America. But if your reaction at all is like, oh my God, this thing from calculus that yeah, I know how to do. Okay, yeah, but like I never. No, this could be an opportunity to actually understand it for the first time. It was for me. I didn't get this calculus stuff until I saw it actually happening in physics. What I'm saying is, so I'm not assuming you already get it. I'm trying to explain it. What I'm saying is if you divide, sorry, well, yeah, if you divide displacement by into a bunch of little delta x's, right? And for each delta x, you ask what the f is at that delta x, and you multiply the f by that delta x, then you're multiplying, the height of a rectangle by the width of a rectangle. And if you add up all those rectangles together, you're getting something close if I multiply each one of these delta x's by an f, then I'm multiplying widths by lengths, and I'm getting areas of rectangles. If I add up all of those rectangle areas together, I'm getting something close to the full area under this curve, which would be close to the full amount of total force times total displacement, total work, right? But of course, as I think you can sort of see from the picture, it's close, but it's not exact, because for each one of these areas, for each one of these rectangles, I'm picking a height that doesn't remain exactly that height for the whole rectangle, because the curve is continuous, right? But if I somehow had a way, of going to the limit as each one of these rectangle widths approached zero, if I could, and I'm not saying I can, but what I want you to see with me is what I want is some way of taking the entire work done, taking an entire displacement, capturing a force value that what I want to know is what's the total work done for an entire displacement for this Sisyphus as he goes up the entire hill. I want to know force times displacement, the number of newtons times the number of meters for the whole thing. My problem is that I know the force is changing as I go. Worse yet, so then I go to myself, all right, fine. So just divide into a bunch of small displacements, multiply the appropriate F by each one of those displacements, add them all up, you're done. Then I said to myself, that's great. And in effect, I'm just going to divide up my entire region into a bunch of rectangles and add up all the rectangles. If the function f were a straight line, like f is a function of x, is the whole premise here. If it were a straight line, or if it were a horizontal line, no problem. But it's a curved line. So no matter how small I make the rectangle, the smaller and smaller I make the rectangles, the closer and closer I get to an accurate depiction of the entire area. But until the rectangles are infinitely thin, I won't be perfect. So what I want these rectangles to be infinitely thin. If I took this process, in other words, if I took the sum to the limit as delta x approaches zero, then I would have the answer to the total work. And from an experimental scientific point of view, I really actually can do that experimentally, because all I have to do is divide the displacements into sizes that are smaller than the smallest interval on my meter stick. And then that means I'm zooming in so close that I'm capturing a constancy of force for each one of those segments. But mathematically, can I do this? Can I do this without an experiment, without measuring tools? Well, this idea. Sorry. I totally see in the chat. I'm sorry. It was 5 minutes ago. But yes, someone is totally writing in the chat, or did write in the chat. Is this like a Riemann sum? Yes. This is a Riemann sum. And I'm saying now, if I take this, good. I mean, I'm glad you see that connection. If I take this Riemann sum to a limit, right? Or I guess technically it becomes a Riemann sum once I take it to the limit. But if I take this idea to the limit, so that I can take this, what seems to become such a straightforward logical idea. Oh, the whole is too big. Treat the whole as the sum of its parts. Then I go, oh, the parts need to be, no matter how small I make the parts, I don't seem to have accomplished my goal. Then they say, all right, then take your parts to the limit. If I do that, if I take the parts to the limit, in general, if in, in general, if some output is a continuous function of input, if some output is a continuous function of input, then we define this thing called the integral. I'm saying all my talk, but I can't promise you this is value. This may be more valuable to some of you than others, but I will tell you it's definitely not a tangent. Everything I've been trying to say for the last whatever, 35, 55 minutes is trying to lead to this point right here. I am saying that the integral that I know that you've worked with a million times in at least one, if not two, calculus classes. The integral, I want you to look at this. My whole point is this bottom is this, like the bottom. Um, this statement at the bottom of the board, let's back up for a second and slow down. This may look very intimidating to some of you. It's a lot of notation. Okay, when I'm here, and it was very intimidating. Some of the, well, whatever, it doesn't matter what I thought of it, but this thing at the bottom is the point, and I'm here to say I'm not here making the assumption that you already get this. This is not a reference this is definitely a reference to something you've seen, and at least one person in the chat clearly has seen this. Thank you very much. But it is what I'm trying to say is you've seen this a million times. It actually is more conceptually approachable than maybe some of you think. Maybe some of you have already given up on this thing. What I'm here to, and maybe some of you are really good at manipulating this thing. Maybe some of you know a lot of rules like U substitutions, integration by parts, et cetera, et cetera. And so you're good at getting answers, but maybe you even know in your hearts that you're getting answers and you don't really know why you care or like what this has to do with the real world or like what any of it means. I was both of those people at various times. I am saying it's not out of nowhere. The left side, the integral of f of x dx, what it actually means, what it means is just what happens when you take a discrete sum to the limit. What it notice what well notice we started off with the concept of a delta x, a small but finite interval of space between position 1 and position 2. Delta x, we said like last week, means possibly small but finite difference in two values of x. Now we've shifted. We've gone to the limit. We've taken delta x to the limit where it is so small that the difference between value x1 and value x2, that difference is actually infinitely small, where x1 and x2 are so close to each other that they seem more like drops of water than like grains of sand. Right? We've shifted from the discrete case of delta x's to the continuous case of dx's. When we shift, So look, compare the right side to the left side. We shifted fx delta x with little i's underneath to f of x times dx. It's still the same thing. It's the output times the input, right? It's the height of a rectangle times the width of a rectangle. If you're talking math graph terms, if you're talking physics, we're talking about some kind of force that depends on position, but we're multiplying the force times the change in position. Either way, it's force times displacement, right? On the right side and the left side of this equation, force times displacement. But the big difference is we were adding up a bunch of small but finite displacements. And then we went to the limit and made those small but finite displacements so small that they're infinitely small, that they're next to each other. They're inseparable. We can't count them anymore. They're just like this schmear, right? We took the widths of the rectangles and made them so small that they're not widths anymore. They're narrow bands. And when we do that, we shift from a jagged, pointy Greek sigma that's meant to stand for sum. We shift from the sigma to the smooth, elongated S, which is the symbol for integral. I don't know about you, but I was doing integrals for semesters and semesters before it ever hit me that the sign for an integral is an S for sum. But it's smooth. I'm not kidding. It's a smooth S. It's a curvy, nice, smooth S rather than the jagged, pointy sigma that we used, for discrete sums. It's not a coincidence. In other words, what I'm really yelling here, I'm not angry at all. I'm like excited, but I believe there's got to be at least one person in the room that, like me, knew how to do integrals but really didn't know what they were or something, or thought that they were antiderivatives or something like that, which notice I have not used that word yet, and there's a reason. What I'm saying here is that what is an integral really? What the heck is an integral really? An integral is a continuous sum of products, always. And please write that down. Oh, I'll write it down. Always, what an integral is, and an integral is a hard thing in math. By the way, the other reason I'm screaming and making a big point of this is derivatives are one thing. They're sort of hard to get your mind around, but then like once you get used to it and the slope of the tangent line and this and that, like people can do derivatives once they get, and maybe even there they don't know what they're doing, but there's rules for derivatives and you can get used to them and the rules always work. Integrals, I think we all know. I don't think I'm alone in saying integrals is another level. Integrals are harder for everybody. Integral for most people. Integrals are harder. It's harder to know what they even are. It's harder to know how to set them up. And as you well know from calculus class, there's a lot of problems you could be given where you don't know which tool to use to solve the integral. You don't know which technique. You don't know if it's going to work. And for all you know, it's not going to work because a lot of integrals actually aren't solvable. That's never true of derivatives. Integrals, if you've ever felt like integrals are harder, you are not alone. You are not crazy. You are not stupid. Integrals are freaking harder. What is, and so most of us just get used to sort of doing them to get by, but we never really face like, what is it that we're doing? Therefore, if anybody like in a physics class ever started saying, you got to set up this integral, you got to turn this problem into an integral, which is kind of what's happening here in the Sisyphus problem, okay? And which will happen a lot in physics 204. If anybody's ever, instead of giving us the integral and say, just solve it, but they said, you've got to now know when to introduce an integral into a problem and solve, that's where most of us, definitely me, would be like, oh, what? Wait, what? Like I actually have to wait, an integral is like an actual thing that like I have to introduce? That was never part of the contract. I am so that okay, and that totally happened to me in college. So I'm telling you what an integral is. What an integral is. Well, it is what this thing at the bottom says right here. What an integral is always, by definition, a continuous sum of products, always, and the products Each product is a little segment of the independent variable, the x-axis, if you're looking at a graph, by the corresponding dependent variable. That is so illegible. Sorry, hold on one second. I know we're almost done, but we are almost done for now. What an integral always is, and why integrals always have like a dx or a dy or a dz or something in them. That's not just like a piece of math notation meant to annoy you, and it's not just like a memorize black magic thing. Every integral in the world is the sum. It's always it's always the concept of take some input in your mind, walk along all the various values of that input as you, i.e., in your mind, walk along an x-axis. Walk along an x-axis, and each place you go, ask yourself, what's the value of y here at this value of the x-axis? Like for this bit of input, what's the output? I.e., walk along the x-axis and look up to the curve, look where the curve is, the function at that point. Always, every integral is, I'm walking a little bit along the input values. I'm asking myself, what is the output value at this place where I'm taking a step? I'm multiplying the two together, the little step along input values by the corresponding appropriate output value. I'm multiplying those together, putting them in my bag, taking the next step, multiplying them together, putting them in my bag. And at the end of the day, when I finish walking, I look at the total that's in my bag, the whole, that is the sum of all of these partial products. And that is what the integral is. The reason the integral is the area under the curve is because area is length times width. The length is the output value. The width is an interval along the input value. So the integral is always just what would happen if you summed up input times output for an entire region described by that function. If you were to just sum up all of those products, but take the process to the limit where each step you're taking is so small that you actually can know the output value to put in, right? This is the whole point, is it's just a sum of products, but we've made the product so small that we can be guaranteed to know what two numbers to multiply together, right? That's what the integral always is. So an integral always is like a continuous. So the integral is what happens when you shift delta x to dx, and by so doing, in other words, you take to the limit, you take delta x to the limit, you get dx, and therefore you swap out the jagged discrete sum that is captured by a sigma, and you substitute in this smooth s that means integral, and you just walk from one value to the next, adding the products as you go. So the integral is always the continuous sum of products. I'm looking at the time. Okay, we have 11 minutes. The integral in math is always the continuous sum of products of input by output. That's why it's always the area under the curve. Okay, but even that starts to sound a little abstract if I'm saying it as a mathematical tool. So what I'm here to tell you now is, if you want to picture the most vivid central example in the physical world for this, if you want to picture the example that in a way sort of motivated this whole way of thinking in the first place, the example is work. Work is not just an example of the integral. Work is the example, is like the central example of the integral that, at least in my case, is what made me understand integrals in the first place. Work is so work in general. So I'm saying if you want one definition of work that covers all of the cases, even the hardest cases where force is varying as a continuous function of position, then what we're saying is the real definition of work from now on. Like, notice again, like, well, well, here, I'll do it like this. One second. I'm just about now. What work is the limit. Okay, so what I'm saying, it's 1033. What I'm saying is that assuming that force varies as a continuous function of position, assuming that capital F, like force, like physics force, is like the output of some situation where position, spatial position, is the input, right? And assuming it's a continuous function, then what work in general is the sum of all the little works. It's the sum of all the delta W's. That is to say, it's the smooth continuous sum of all the dW's, right? Like notice, well, yeah, right? And what does that mean? It means in general, what work is the integral from one value of x to another value of x, like is the definite integral from one value of x to another value of x of force dot producted with dx, all assuming that the force is a continuous function of x. Integral, in other words, integral is just this, I mean, work is just the space integral of force. Technically, the lesson, we have 5 minutes left. I'm going to start trying to apply this to numbers now. I know that will make things more satisfying. And of course, we'll pick up on this, we'll just do concrete examples from here on all Wednesday. I know for some of you, for many of you, the concrete is much more helpful. I get that. Technically, the lesson of today is that work is an integral, okay? But secretly, truly, honestly, one of the reasons I always take so long with this is yes, technically, I'm teaching you that work is the integral of force. And technically, you've had 2 years of calculus so that you're supposed to know what it means when I say integral. So technically, since you already know what integrals are, now you understand that work is an integral. So whenever we do, and we will have to, problems where the force varies continuously as a function of displacement, you'll know that to calculate the work, we're literally, and therefore to calculate the potential energy and all the other stuff we talked about last Wednesday, you now, from now on, like, know, oh, I've got to do an integral, or I've got to understand integrals to do this. But secretly, honestly, what I'm really trying to do today for many of you, not all of you, but many of you, what I'm really trying to say is, you know what? If you're kind of understanding what work is at this point in the semester, if you kind of get that work is the force multiplied by the displacement, then picturing work as an integral might help you for the first time really start to get in your mind around really what an integral is. The classical example of work of an integral is the physics integral known as work. For me, the physics makes the calculus actually easier to get my mind around. That is not true of all of you, but it may be true of some of you. So it's another plug for don't give up on calculus yet. And also don't think that you know calculus just because you can solve problems. The question is, can we set up calculus problems to apply to the real world? This is where like that sort of begins. Now, we have 3 minutes. So hopefully that was helpful to some. Sorry. I'm seeing in the chat. Well, okay, great question in the chat. Wait, I want to look at number. Hold on. I know we have 3 minutes. It's such a great question. Okay, I'm going to answer the question in the chat. That may be it for the class. Let me also just say, because I know we're going to run out of time. I'm very aware that for some of you, this doesn't mean anything until we do concrete examples. I know you're desperate to see the concrete. That is totally what we'll do Wednesday. It's not that I don't get that. I, I'll just leave it at like that's an acknowledgement, okay? But I find year after year that there's usually a couple of people, whatever, you get my point. All right, so we'll get to the concrete examples, back to the Sisyphus. Well, actually, let me say, hold on. I want to answer this question in the chat, but wait, we have 3 minutes. Actually, okay, let me make this a little bit concrete. So I'm looking. In fact, I can. We have 2 minutes. I'm watching. I promise. I will not let you go late. Like just so that we can have some concreteness for those of you who want, me to land a plane. Like I'm looking at this problem right here. The whole key is part C, where it says C1, Roman numeral, write the force of Sisyphus push as a function of his position. Well, the function would be F Sisyphus equals 990 minus 30 times X, right? I mean, it's that, and which I think probably a lot of you got right? But then, I mean, it sort of gives you a hint there. It's not 990 minus 30 times X. But then the point is that's a function now, right? That's saying no matter what value of X you have, you plug in and you'll get the value of force. And the whole implication of that is even if you plugged in a value of X that was smaller than 1, it would spit out some kind of value. So to get the total work done, to answer the question, C2, what you literally do is do the integral of 990 minus 30x. Now that's really 2 integrals. It's the integral of 990 dx minus the integral of 30x dx. How do you do those integrals? That's where your calculus class comes in. I mean, I haven't said yet in this class, but I think you do the antiderivatives to do those integrals, right? You do the derivatives backwards. Now I'm going to say 2 quick things because there's 1 minute left. First of all, I want to answer the question in the chat. The chat question is, by lowercase d, do I mean displacement? So I want to be honest. It's a great, super important question, but the answer is no. By D, I mean the same D that they mean in math class. By X, I mean position, yes. So remember in physics up until now, delta X would mean displacement. The X2 minus X1, the difference in 2 values of X means displacement, right? But now when I say dx, what I really mean is infinitely small displacement in X. If that makes the D stands for differential, like from math class. I'm using D to say that the delta got infinitely small. So dx, yes, together dx does mean infinitely small displacement. And and it's 10:40. One last thing I just want to say, to solve this, to get the answer, which we'll pick up on Wednesday, yes, you would do antiderivatives, but please note, if there's another takeaway to this entire 75 minutes, it's that the definition of the integral is not the antiderivative. The reason and I'm going to start with this statement on Wednesday, that's not the definition. The definition of the integral is the continuous sum of products. What is an integral? The continuous sum of products. How do we solve for integrals? It turns out we use antiderivatives. Okay, that's just like, what is work? Force times displacement. What's the purpose of work, or how do we solve for it? It transfers energy. Okay, it's triple equal sign versus double equal sign. I'll pick up with that statement on Wednesday. But yes, okay, I'll leave it at that. But you guys have been very, very patient. You're continuing to be very patient. See you and okay. I'm turning off the recording. I'm stopping the screen. Just stop the share. I'm done. Like you can go, you can go. But if anybody wants,
Thank you.
thank you, thank you. Okay, wait, bye. Have a good day. Have a good day. Stop the share. Stop.